Hello there, and welcome to another gentle journey into the natural world. I'm Charles, and tonight we're settling in to explore one of nature's most soothing and mysterious phenomena: rainfall. For the next hours, we'll drift through clouds and discover the hidden wonders that rain carries with it, from the invisible dance of water molecules miles above us to the earthy perfume it releases when touching dry ground. Rain has accompanied life on Earth for billions of years, and yet it holds secrets that scientists are only now beginning to understand. Tonight, we'll wander through 100 gentle mysteries about rainfall, each one revealing something extraordinary about this familiar yet endlessly fascinating aspect of our world. Some mysteries involve the science behind each droplet's formation, while others explore the sounds, smells, and strange occurrences that make rain such an enchanting presence in our lives. If these explorations help you unwind at the end of your day, I invite you to share your thoughts in the comments below, or simply settle in and let the mysteries of rainfall carry you toward peaceful rest. But for now, let us begin our journey through the clouds, where every raindrop tells a story that began long before it ever touched the earth. The first mystery of rain begins miles above our heads, in a realm where temperature and pressure create conditions entirely unlike anything we experience on the ground. Water vapor rises from oceans, lakes, rivers, and even from the leaves of plants, carried upward by warming air that expands and becomes lighter than the atmosphere around it. This invisible moisture travels higher and higher, sometimes reaching altitudes where commercial aircraft cruise, entering regions where the air grows cold enough to transform vapor back into liquid or ice. As water vapor ascends into these cooler layers of atmosphere, it encounters microscopic particles suspended in the air. These tiny specks might be grains of dust blown from distant deserts, crystals of salt carried up from ocean spray, particles of smoke from wildfires, or even pollen released by forests far below. Each particle, though invisible to our eyes individually, becomes something remarkable in the presence of water vapor. It becomes what scientists call a condensation nucleus, a foundation upon which water molecules can gather and cling. The second mystery involves the delicate architecture of how water droplets form around these microscopic seeds. A single particle of dust might measure only a few millionths of a meter across, yet it possesses a surface where water molecules can bond. The first molecules to attach create a film so thin it would take thousands of such layers to equal the thickness of a human hair. More molecules join, attracted by the hydrogen bonds that make water such a remarkable substance. These bonds, weak individually but powerful in numbers, draw molecule after molecule into an expanding sphere. The third mystery emerges as these droplets grow within the cloud. They don't simply remain suspended in place, waiting to fall. Instead, they drift and tumble through the cloudy atmosphere, colliding with other droplets in a process scientists call coalescence. Each collision offers a chance for two droplets to merge into one larger sphere. A droplet that began as a microscopic gathering around a single dust particle might collide with hundreds or thousands of other droplets during its time in the cloud, growing from invisibly small to a size that can finally overcome the updrafts holding it aloft. The fourth mystery concerns the shape of falling raindrops, which differs dramatically from the teardrop shape so often depicted in drawings and illustrations. When raindrops are very small, measuring less than 1 millimeter across, surface tension pulls them into perfect spheres, like tiny liquid planets falling through the sky. As drops grow larger, reaching 2 or 3 millimeters in diameter, air resistance begins to affect their shape. The bottom of the drop encounters more resistance as it falls, causing it to flatten while the top remains rounded, creating a shape more like a hamburger bun than a teardrop. The fifth mystery involves what happens when raindrops grow even larger. Once a raindrop reaches about 4 or 5 millimeters across, the forces acting upon it become too great for surface tension to maintain its integrity. The bottom continues to flatten and develop an indentation, almost like a small parachute. Eventually, the drop becomes so distorted that it breaks apart, splitting into several smaller droplets that continue their descent independently. This constant process of growth and splitting helps explain why raindrops tend to fall within a certain size range, rarely growing larger than about 6 millimeters in diameter. The sixth mystery explores how many tiny cloud droplets must come together to create a single raindrop. The numbers are staggering. A typical cloud droplet measures perhaps 20 micrometers across, while a small raindrop might be 2 millimeters in diameter. To create that raindrop through collision and coalescence requires roughly 1 million cloud droplets to merge together. This process happens continuously within rain clouds, with countless droplets colliding, merging, breaking apart, and colliding again in an intricate dance governed by air currents, temperature gradients, and the ever-present pull of gravity. The seventh mystery involves the alternative pathway to rainfall that doesn't require millions of collisions. In clouds where temperatures drop below freezing, water can form ice crystals rather than liquid droplets. These crystals begin their existence with six-sided symmetry, reflecting the hexagonal arrangement of water molecules in ice. As crystals grow, they pull water vapor from the surrounding air, sometimes growing large enough to fall without needing to collide with millions of other crystals. When these ice crystals descend through warmer air, they melt and become raindrops, often producing rain more efficiently than the collision coalescence process alone. The eighth mystery concerns how much water actually falls during rainfall. 1 inch of rain across a single acre of land deposits 27,154 gallons of water. That's enough to fill hundreds of bathtubs, all from rain falling across an area smaller than a football field. When rain falls across entire watersheds spanning thousands of square miles, the volumes become almost incomprehensible, with billions of gallons returning from the atmosphere to the Earth's surface in a single storm system. The ninth mystery involves the speed at which raindrops fall. Unlike objects falling in a vacuum, where all items accelerate at the same rate regardless of their mass, raindrops quickly reach a terminal velocity where air resistance balances the downward pull of gravity. Small drizzle drops might fall at only about 2 meters per second, roughly walking speed, taking many minutes to descend from cloud base to ground. Larger raindrops can reach speeds of 9 meters per second, falling fast enough that their impact creates that satisfying patter against windows and rooftops, yet still slow enough that we can often watch individual drops streak past our vision. The 10th mystery explores why rain sometimes falls from seemingly clear skies. This phenomenon, known as virga, occurs when precipitation forms within a cloud and begins falling, but encounters air so dry below the cloud that droplets evaporate completely before reaching the ground. Observers see ghostly curtains of rain descending from the cloud base, fading to nothing as they fall through the thirsty air. These phantom rains, though they never wet the ground, still play important roles in atmospheric processes, cooling the air through which they fall, and sometimes triggering gusty winds when the cooled air descends rapidly. The 11th mystery involves the global water cycle and how the same water molecules have been falling as rain for billions of years. A water molecule in today's rainfall might have last fallen as rain decades ago, or perhaps centuries past. It might have spent time locked in glacial ice during the last ice age, or dissolved in ancient seas when dinosaurs walked the earth. Each molecule follows an endless journey from surface to atmosphere and back again, driven by solar energy that evaporates water and atmospheric patterns that transport moisture across continents and oceans. The 12th mystery concerns how long water typically spends in the atmosphere during each cycle. On average, a water molecule evaporates from Earth's surface and returns as precipitation within about 9 days. This relatively brief atmospheric residence time means that the atmosphere holds only about 1% of Earth's fresh water at any given moment. Yet this small fraction, constantly cycling, delivers all the rain that sustains terrestrial ecosystems, fills rivers, and replenishes groundwater. The 13th mystery explores the formation of that distinctive smell associated with rainfall, a sense so universal that scientists coined a special term for it, petrichor. This word, created in 1964 by 2 Australian researchers, combines the Greek words for stone and the ethereal fluid that supposedly flowed in the veins of gods. The name captures something essential about the experience, that sense of the earth itself breathing out its essence when rain arrives after dry periods. The 14th mystery involves the chemistry behind petrichor's most powerful component, a compound called geosmin. This organic molecule is produced by soil-dwelling bacteria called actinomycetes, particularly species within the genus Streptomyces. These ancient microorganisms have lived in soil for hundreds of millions of years, producing geosmin as part of their metabolic processes. The compound accumulates in dry soil during rainless periods, waiting patiently for the moment when falling droplets will release it into the air. The 15th mystery concerns human sensitivity to geosmin, which ranks among the most remarkable sensory capabilities our species possesses. We can detect geosmin at concentrations as low as 5 parts per trillion, meaning our noses can identify the presence of this compound, even when it represents only 5 molecules among every trillion molecules of air. This extraordinary sensitivity surpasses our ability to detect most other scents, suggesting that recognizing the smell of rain might have provided significant survival advantages to our ancestors. The 16th mystery explores why humans evolved such acute sensitivity to geosmin. Scientists theorize that this ability helped our ancestors locate water sources, particularly in arid environments where finding water meant the difference between life and death. The scent of geosmin signals not just the presence of recent rain, but also indicates areas where water collects and soil retains moisture. Even today, this ancient sensory connection persists, explaining why the smell of rain often evokes feelings of comfort, relief, and well-being that transcend simple pleasant sensation. The 17th mystery involves the mechanism by which rain actually releases geosmin into the air. When raindrops strike porous surfaces like dry soil, they trap tiny air bubbles beneath them. These bubbles, compressed by the impact, shoot upward through the water droplet like microscopic geysers. As they burst through the top of the droplet, they create ultrafine aerosol particles containing geosmin and other compounds from the soil surface. These aerosol droplets, measuring only micrometers across, can remain suspended in air for extended periods, carrying the scent of rain far from where the drops actually fell. The 18th mystery concerns the other components that contribute to petrichor's complex aroma. Besides geosmin, falling rain releases plant oils that accumulated on surfaces during dry periods. These volatile compounds, including fatty acids like stearic and palmitic acid, were secreted by plants as protective measures during drought. The oils create a waxy coating that helps plants conserve water and also prevents seeds from germinating when moisture is insufficient for survival. When rain finally arrives, these oils are liberated from leaves, bark, and soil, adding subtle, waxy, earthy notes to petrichor's overall scent profile. The 19th mystery involves ozone, the third major component of rain's characteristic smell. Lightning produces ozone high in the atmosphere by splitting oxygen molecules and allowing some atoms to recombine into the 3-atom form of oxygen we call ozone. This sharp, clean scent can travel ahead of storms, giving sensitive observers the ability to quite literally smell approaching rain before the first drops fall. Ozone's presence in the air creates that distinctive pre-storm scent, a smell that signals change is coming and rain will soon arrive. The 20th mystery explores the evolutionary relationship between geosmin producing bacteria and certain tiny arthropods called springtails. Recent research suggests that Streptomyces bacteria produce geosmin not just as a metabolic byproduct, but as a deliberate signal to attract these small creatures. Springtails feed on the bacteria and then disperse bacterial spores in their droppings, helping Streptomyces colonize new areas of soil. This 500-million-year-old partnership represents one of the oldest known examples of chemical communication between organisms, with the scent of rain serving as the message that connects them. The 21st mystery concerns why some animals can detect rain from remarkable distances. Camels, for instance, can reportedly detect water sources from up to 80 kilometers away by following the scent of geosmin carried on desert winds. This ability allows them to locate oases and waterholes across vast expanses of seemingly empty desert, navigating by following an aroma that most other mammals can detect, but not at such extreme distances. Other desert-dwelling creatures show similar sensitivities, using geosmin as a chemical beacon, guiding them toward moisture and life-sustaining water. The 22nd mystery involves how rain sounds create such powerful effects on human sleep and relaxation. The acoustic signature of rainfall contains frequencies across a broad spectrum, from the low rumbles of distant thunder to the high patter of drops striking different surfaces. This mixture of frequencies functions much like white noise, masking other environmental sounds that might otherwise disturb sleep or concentration. The randomness of rain sounds, with no predictable pattern to capture attention, allows our minds to rest without trying to process or interpret what we hear. The 23rd mystery explores why rain sounds feel more natural and pleasant than artificial white noise. While electronic white noise contains equal intensity across all frequencies, rain sounds have subtle variations and organic qualities that our brains perceive as non-threatening. The rhythmic yet unpredictable pattern of drops striking surfaces creates a soundscape that engages our auditory processing just enough to mask disruptive noises, but not so much that it demands conscious attention. This sweet spot of acoustic engagement helps explain why rain sounds have become among the most popular choices for sleep and relaxation recordings. The 24th mystery concerns the different acoustic signatures created by various types of rainfall. Light drizzle produces a soft, high-frequency patter, while heavy rain generates deeper, more powerful sounds as larger drops impact surfaces with greater force. Rain falling on different materials creates distinct sonic textures, from the metallic ring of drops hitting tin roofs to the soft absorption of rain sinking into soil or striking foliage. These variations in rain's acoustic landscape mean that no two rainstorms sound exactly alike, providing endless variety within a consistently soothing audio experience. The 25th mystery involves the psychological associations humans develop with rain sounds. Many people report feeling safe, protected, and cozy when hearing rain, particularly when they're indoors listening to precipitation falling outside. This emotional response likely connects to primal experiences of shelter, when being inside during storms meant safety from the elements. The sound of rain on a roof or against windows serves as auditory confirmation that we're protected, triggering relaxation responses that helped our ancestors rest securely when environmental conditions made outdoor activity dangerous or uncomfortable. The 26th mystery explores how rain sounds activate the parasympathetic nervous system, the part of our autonomic nervous system responsible for rest, digestion, and recovery. Natural sounds, including rainfall, have been shown to shift the balance between sympathetic fight or flight activation and parasympathetic rest and digest functions. This physiological shift manifests as lowered heart rate, reduced blood pressure, and decreased production of stress hormones, creating conditions optimal for sleep and relaxation. The 27th mystery concerns the phenomenon of pink noise, a type of sound where intensity decreases as frequency increases. Rain sounds often contain pink noise characteristics, with more energy in lower frequencies than in the highs. Research suggests that pink noise may enhance sleep quality more effectively than pure white noise, possibly by better matching the natural frequency distribution of environmental sounds our ancestors evolved hearing. Rain's pink noise qualities might explain why it proves particularly effective for promoting deep, restorative sleep. The 28th mystery involves how rain sounds can improve focus and concentration during waking hours. The acoustic masking effect that helps block disruptive noises during sleep also functions when we need to concentrate on mental tasks. By creating a consistent sound floor that masks intermittent distractions like conversations, traffic, or unexpected noises, rain sounds help maintain the steady attention required for reading, writing, studying, or other cognitive work. Many people report that listening to rain while working feels less mechanical and more pleasant than using artificial noise generators. The 29th mystery explores the concept of acoustic masking and how rain sounds achieve it so effectively. Our brains constantly process environmental sounds, even during sleep, to detect potential threats or important signals. Sudden or unexpected noises can trigger arousal responses that interrupt sleep or break concentration. Rain sounds function as auditory camouflage, creating a relatively constant acoustic environment where smaller disruptions become less noticeable. The slight variations in rain sounds also prevent our brains from habituating completely, maintaining a subtle level of acoustic interest that keeps the masking effect strong. The 30th mystery concerns why some people find rain sounds more relaxing than others. Individual differences in auditory processing, life experiences with rain, and personal associations all influence how we respond to rainfall's acoustic qualities. People who grew up in climates with frequent rain might associate these sounds with childhood comfort and security, while those from arid regions might find rain unfamiliar or even slightly unsettling at first. These personal variations remind us that while rain holds universal mysteries, our individual experiences with it remain unique and deeply personal. The 31st mystery involves the strange phenomenon of fish and frogs occasionally falling from the sky during rainstorms. While this sounds like folklore, well-documented cases exist throughout history and around the world. In 1894, newspapers in Bath, England, reported a rain of tadpoles. More recently, a storm in Japan in 2009 brought a shower of minnows down on the city of Ishikawa. These bizarre events have puzzled observers for centuries, leading to various supernatural explanations before scientists developed more plausible theories about their causes. The 32nd mystery explores how animals end up falling with rain. The most accepted scientific explanation involves waterspouts, essentially tornadoes that form over bodies of water. These rotating columns of wind can reach speeds of 100 miles per hour, powerful enough to lift small aquatic creatures from ponds, lakes, or coastal waters. As the waterspout loses energy or moves over land, it releases its contents, including any animals swept up during its formation. This process can deposit fish, frogs, or other small creatures miles from their original habitats, creating the appearance of animals raining from the sky. The 33rd mystery concerns why reports of animal rain typically describe only one species falling at a time. Witnesses report rains of fish or rains of frogs, but rarely mixtures of different creatures. Scientists explain this uniformity through the physics of falling objects. Items of similar size, shape, and weight tend to fall at similar speeds and be deposited together. As wind currents lose energy, they drop heavier objects first, followed by progressively lighter ones. This natural sorting process means that animals of similar mass would likely fall in the same location, creating the species-specific rains that witnesses describe. The 34th mystery involves coloured rains, particularly the phenomenon of red rain that has been reported since ancient times. The most famous recent case occurred in Kerala, India in 2001, where bright red rain fell for several weeks, staining clothes and buildings. Initial theories suggested the red colour came from dust blown from distant deserts, but microscopic analysis revealed something more intriguing. The rain contained cells of a red algae called Trentipolia, rich in carotenoid pigments. How such vast quantities of this organism reached cloud heights remains a subject of ongoing research. The 35th mystery explores how desert dust can travel thousands of miles to colour rain far from its source. The Sahara Desert regularly sends dust clouds across the Atlantic Ocean, sometimes reaching as far as the Americas. When this airborne dust encounters precipitation systems, it becomes incorporated into raindrops, creating yellow or red-coloured rain, depending on the mineral composition of the source material. Similar patterns occur with dust from the Gobi Desert colouring rain across Asia, demonstrating the atmosphere's ability to transport materials across entire continents. The 36th mystery concerns black rain, which can result from different sources. Volcanic eruptions can inject massive quantities of ash into the atmosphere, which then falls with precipitation as dark, sooty rain. Industrial pollution has also created black rain, most notably during the height of coal-burning industrialization in Europe, when soot-filled rain would darken sheep's wool and stain buildings. More recently, burning oil wells during the Gulf War in 1991 produced black rain and snow that fell as far away as India, demonstrating how local events can affect precipitation over vast regions. The 37th mystery involves mysterious gelatinous material sometimes reported falling with rain, known as star jelly. Historical accounts of this substance date back centuries, with observers describing translucent, jelly-like blobs appearing after rain. While folklore attributed star jelly to meteors or shooting stars, modern investigations suggest it might be algae, bacterial colonies, or biological material from decomposing organisms that becomes more noticeable when wet. The true nature of star jelly remains somewhat mysterious, as many historical reports lack the detailed chemical analysis needed to definitively identify the substance. The 38th mystery explores the wettest places on Earth and the extraordinary rainfall they receive. Mawsynram in northeastern India holds the record for highest average annual rainfall, receiving roughly 11.5 meters of rain each year, equivalent to more than 450 inches. This remarkable precipitation results from the region's position along the path of moisture-laden monsoon winds that rise rapidly as they encounter steep mountain slopes, forcing moisture to condense and fall as torrential rain. The 39th mystery concerns the driest inhabited places on Earth, where rain becomes so rare its arrival causes celebration. The Atacama Desert in Chile holds regions where measurable rainfall occurs only once or twice per century. Some areas have gone decades without any recorded precipitation, creating landscapes so Mars-like that space agencies use them to test equipment designed for the red planet. When rain does finally arrive in these hyper-arid regions, it can trigger the dramatic blooming of dormant seeds that have waited years or even decades for moisture. The 40th mystery involves the paradox of Antarctica, a continent covered in ice but receiving less precipitation than many deserts. The interior of Antarctica gets only about 2 inches of rainfall equivalent per year, making it technically a desert despite being buried under ice sheets kilometers thick. The extreme cold prevents the atmosphere from holding much moisture, limiting precipitation, even though water in solid form covers the landscape. This demonstrates that rainfall patterns depend on atmospheric conditions, not on the presence or absence of water on the surface. The 41st mystery explores seasonal monsoons and the dramatic shifts in weather patterns they create. Monsoon systems develop when temperature differences between land and ocean create powerful wind patterns that reverse direction with the seasons. During summer, warm land masses draw moisture-laden air from cooler oceans, producing months of heavy rainfall. Winter brings reversed winds that blow dry air from continents toward the oceans. These seasonal patterns affect billions of people across Asia, Africa, and other regions, making monsoon rains critical for agriculture and water supplies. The 42nd mystery concerns how El Niño and La Niña cycles influence global rainfall patterns. These periodic changes in Pacific Ocean temperatures affect atmospheric circulation patterns worldwide, bringing drought to some regions while causing flooding in others. During El Niño years, warm water in the eastern Pacific disrupts normal weather patterns, often bringing rain to typically dry areas while reducing precipitation in normally wet regions. La Niña creates opposite effects, demonstrating how oceanic conditions thousands of miles away can determine whether your region experiences drought or deluge. The 43rd mystery involves urban heat islands and how cities alter local rainfall patterns. Urban areas, with their extensive pavement, buildings, and reduced vegetation, absorb and retain more heat than surrounding countryside. This increased temperature can enhance convection, the rising of warm air that helps trigger thunderstorms. Studies have found that cities often receive more rainfall than nearby rural areas, particularly during late afternoon and evening when urban heat islands reach their peak intensity. Some cities show measurably higher weekend rainfall than weekday precipitation, possibly related to weekly patterns in air pollution and traffic. The 44th mystery explores how forests influence rainfall through a process called evapotranspiration. Trees pull water from soil through their roots and release it as vapor from their leaves, effectively pumping moisture from ground to atmosphere. Large forests can transpire enormous quantities of water daily, contributing significantly to local and regional humidity. This moisture becomes available for rain formation, creating feedback loops where forests help generate the precipitation that sustains them. Deforestation can disrupt these patterns, potentially reducing rainfall in affected regions and areas downwind. The 45th mystery concerns atmospheric rivers, narrow bands of concentrated moisture in the atmosphere that transport enormous quantities of water vapor. These flowing corridors, sometimes stretching thousands of kilometers long but only a few hundred kilometers wide, can carry more water than the flow of the largest terrestrial rivers. When atmospheric rivers make landfall, they often produce intense, prolonged rainfall that can lead to flooding, but also provides crucial water supplies to regions along the west coasts of continents. The 46th mystery involves the beautiful phenomenon of sun showers, when rain falls while the sun remains visible in the sky. This occurs when wind carries rain from a distant cloud into areas where skies remain clear, or when small rain showers drift away from the main body of a storm cloud. Many cultures have special names and folklore surrounding sun showers. From the American South's devil is beating his wife to various international explanations involving foxes getting married or witches combing their hair. The meteorological reality proves equally enchanting, as sun showers often produce vivid rainbows where sunlight refracts through falling droplets. The 47th mystery explores rainbow formation and the specific conditions required for these colorful arcs to appear. Rainbows occur when sunlight enters raindrops, reflects off the back inner surface, and exits at an angle that separates white light into its component colors. The observer must be positioned with the sun behind them and rain falling ahead, with the sun's angle above the horizon below 42 degrees. Each raindrop creates its own rainbow effect, but we perceive a continuous arc because millions of drops at specific angles relative to our viewpoint produce the same colors simultaneously. The 48th mystery concerns double rainbows and the reversed order of colors in the secondary arc. When light reflects twice inside raindrops instead of once, it creates a fainter secondary rainbow outside the primary arc. This double reflection reverses the color sequence, placing red on the inside of the secondary rainbow and violet on the outside. The region between the primary and secondary rainbows appears darker than surrounding sky, a zone called Alexander's Band, where fewer light rays reach the observer's eye due to the geometry of light paths through raindrops. The 49th mystery involves moonbows, rare nighttime rainbows illuminated by moonlight rather than sunlight. These ethereal arcs typically appear colorless to human eyes because moonlight is too dim to activate the color-sensing cone cells in our retinas, leaving only the more sensitive but colorblind rod cells to perceive the light. However, long exposure photography can reveal that moonbows contain the same spectrum of colors as their daytime counterparts, demonstrating that the limitation lies in our eyes rather than the phenomenon itself. The 50th mystery explores why rain feels warmer in summer storms, but cold during winter precipitation. This perception reflects the ambient temperature difference between raindrops and our skin. Summer rain falls through warm air, so drops might be only slightly cooler than body temperature, or even pleasantly tepid. Winter rain descends through cold air, arriving chilled and feeling icy against warmer skin. The same physical process of heat transfer feels dramatically different depending on the starting temperatures involved, reminding us that our perception of rain's character changes with seasons and contexts. The 51st mystery concerns acid rain and how human activities alter the chemistry of precipitation. When sulfur dioxide and nitrogen oxides released by burning fossil fuels mix with atmospheric water vapor, they form sulfuric and nitric acids. These compounds make rain more acidic than normal, with pH values sometimes dropping below 5, comparable to vinegar. Acid rain can harm aquatic ecosystems, damage vegetation, and corrode buildings and monuments. While regulations have reduced acid rain in many regions, it remains a concern wherever industrial emissions go uncontrolled. The 52nd mystery involves the speed at which rain clouds move across the sky. Cloud movement depends on wind speed at their altitude, which often differs dramatically from surface winds. Clouds might appear to drift lazily overhead while actually racing along at 50 or 60 miles per hour, carried by atmospheric currents invisible to ground observers. The apparent slow motion results from distance, the same perceptual effect that makes high-flying aircraft seem to crawl across the sky despite traveling at hundreds of miles per hour. The 53rd mystery explores why some rainstorms produce thunder and lightning while others fall silently. Thunderstorms require strong updrafts that carry water droplets and ice crystals up and down through clouds repeatedly. These movements create electrical charge separation, with positive charges accumulating in upper cloud regions and negative charges concentrating lower. When the voltage difference becomes great enough, it overcomes air's electrical resistance, creating lightning and the resulting thunder. Gentle, steady rain typically forms in clouds without these violent updrafts, producing precipitation without the electrical drama of thunderstorms. The 54th mystery concerns how lightning creates thunder through a process that involves heating air to temperatures exceeding 50,000 degrees Fahrenheit in microseconds. This extreme rapid heating causes explosive expansion of air along the lightning channel, creating the shock wave we hear as thunder. The sound varies from sharp cracks for nearby strikes to long rumbles for distant lightning, with the rolling character resulting from sound waves traveling different distances from various parts of the lightning bolt's branching path. The 55th mystery involves calculating distance to lightning using the time delay between seeing the flash and hearing thunder. Light travels so quickly that we see lightning essentially instantaneously. Sound travels much slower, about 1 mile every 5 seconds. By counting seconds between flash and thunder, then dividing by 5, you can estimate your distance from the lightning strike in miles. This simple technique helps gauge whether storms are approaching or moving away, useful information for deciding whether to seek shelter. The 56th mystery explores why rain sometimes falls in sheets or curtains visible from a distance. This effect, particularly noticeable over open water or flat terrain, results from perspective and lighting conditions that make rainfall boundaries distinct. When sunlight illuminates rain falling from one cloud while surrounding areas remain dry, the contrast creates sharply defined curtains of precipitation. These visual boundaries mark where updrafts feeding the cloud create sufficient moisture concentration to produce rain, demonstrating that precipitation often varies dramatically across small distances. The 57th mystery concerns why puddles form in some spots but not others after identical rainfall. Surface characteristics determine how water behaves when reaching ground. Impervious materials like pavement prevent infiltration, allowing water to pool in low spots. Soil type, vegetation density, slope, and compaction all influence whether rain soaks into earth or runs off. Even small variations in ground elevation concentrate flowing water, explaining why puddles consistently form in particular locations after each rain, creating temporary pools that reflect sky and clouds like fleeting mirrors scattered across the landscape. The 58th mystery involves the peculiar sensation of phantom raindrops, when you feel certain you were struck by rain despite clear skies overhead. This puzzling experience usually results from insects flying past, leaves or seeds falling, or tiny droplets condensing on surfaces and then dripping. Sometimes individual raindrops from distant clouds drift far from their source, arriving so sparsely that recipients question whether rain is actually falling. These isolated drops, meteorological wanderers separated from their shower, can indeed create that distinct feeling of rain, beginning without subsequent drops confirming the impression. The 59th mystery explores how raindrops maintain their internal structure during freefall. Despite tumbling through air at several meters per second, raindrops don't slosh around internally the way you might expect. Surface tension creates a membrane-like barrier that holds the liquid together, while internal viscosity prevents turbulent mixing. The result is that molecules throughout the drop move together as a coherent unit rather than churning chaotically. This cohesion allows drops to survive their descent largely intact until they strike surfaces or grow large enough The aerodynamic forces overcome surface tension's unifying influence. The 60th mystery concerns why rain makes certain surfaces slippery while improving traction on others. Smooth materials like painted wood, metal, or polished stone become dangerously slick when wet because water fills microscopic surface irregularities that normally provide friction. The thin water layer then acts as a lubricant between shoe sole and surface. Conversely, rain often improves traction on sandy or dusty surfaces by binding particles together, preventing them from rolling like tiny ball bearings underfoot. This dual effect explains why rain makes some outdoor activities treacherous while actually aiding others. The 61st mystery involves how rainwater can remain surprisingly pure despite falling through miles of atmosphere. While rain does collect some particles and gases during descent, the resulting chemical composition often remains far cleaner than surface water. This purity made rainwater historically valuable for drinking, washing, and industrial processes requiring low mineral content. However, modern atmospheric pollution has reduced rainwater's natural cleanliness in many regions, adding another dimension to rain's changing relationship with human civilization. The 62nd mystery explores the practice of rain harvesting and how simple systems can collect substantial water volumes. A modest roof receiving 1 inch of rain across 1,000 square feet will catch about 600 gallons of water. Throughout history, civilizations have developed sophisticated methods to capture, store, and utilize rainwater, from ancient cisterns carved into bedrock to modern systems with filters and treatment equipment. As fresh water becomes increasingly precious, renewed interest in rain harvesting demonstrates how this ancient practice remains relevant for supplementing water supplies. The 63rd mystery concerns why rain sometimes appears to fall upward during strong thunderstorms. This optical illusion occurs when powerful updrafts within storm clouds overcome gravity's downward pull on smaller raindrops and cloud droplets. These ascending air currents can reach speeds exceeding 100 miles per hour, strong enough to carry precipitation upward despite gravity. Observers witnessing this phenomenon see rain or hail that briefly reverses direction before gravity eventually prevails, demonstrating the tremendous energy contained within severe thunderstorms. The 64th mystery involves virga again, but this time exploring how these phantom rains affect local weather even without reaching ground. When virga evaporates, it cools surrounding air through the same process that makes evaporating sweat cool our skin. This cooled air becomes denser and sinks rapidly, sometimes creating gusty winds called microbursts. These descending currents can reach speeds dangerous to aircraft during landing and takeoff, demonstrating that precipitation need not reach surface to affect conditions at ground level. The 65th mystery explores the formation of hail, frozen precipitation that forms through a completely different process than ordinary rain. Hailstones begin as ice crystals or frozen raindrops that get caught in powerful thunderstorm updrafts. These updrafts carry the embryonic hailstones upward into extremely cold cloud regions, where supercooled water droplets freeze onto their surfaces, adding layers like an onion. The stones can cycle up and down through the cloud multiple times, accumulating layer after layer of ice until they grow too heavy for updrafts to support, finally falling to earth as hail rather than rain. The 66th mystery concerns the largest hailstones on record, which seem impossible given that ice typically breaks apart when impacted. The record holder in the United States, which fell in South Dakota in 2010, measured 8 inches in diameter and weighed nearly 2 pounds. Such massive hailstones require exceptionally powerful updrafts to keep them aloft long enough to grow so large. and their survival during the fall depends on not tumbling in ways that would cause them to shatter. Finding intact giants like these provides glimpses into the extreme conditions within supercell thunderstorms. The 67th mystery involves the relationship between rain and soil erosion, a process that can seem counterintuitive. While we think of rain as nourishing earth, heavy rainfall can actually strip away soil through splash erosion and runoff. Individual raindrops striking bare soil with enough force to dislodge particles, which then wash away with flowing water. Over time, this process can remove topsoil faster than natural processes rebuild it, creating environmental problems that have plagued agriculture throughout history. Vegetation helps protect soil by absorbing raindrop impact and holding earth in place with root systems. The 68th mystery explores how rain shapes landscapes over geological timescales. Water flowing across land surfaces carves valleys, deepens canyons, and gradually wears down mountains. Rain dissolves minerals from rocks, carrying them in solution towards seas, where they eventually precipitate or concentrate. Over millions of years, these processes dramatically transform terrain, demonstrating that gentle rain, through persistent accumulated action, wields power comparable to more obviously violent geological forces like earthquakes and volcanic eruptions. The 69th mystery concerns the phenomenon of rain shadows, regions that receive little precipitation because they lie downwind of mountains. When moisture-laden air rises over mountain ranges, it cools and releases precipitation on the windward slopes. By the time air descends the lee side, it has lost most moisture, creating arid conditions. The Atacama Desert owes its extreme dryness partly to being situated in the rain shadow of the Andes Mountains, while similar effects create desert conditions in numerous locations worldwide. The 70th mystery involves why forecasting rain remains challenging despite modern technology. Precipitation results from interactions between multiple atmospheric variables: temperature, pressure, humidity, and wind patterns at various altitudes. Small changes in any factor can determine whether clouds produce rain or dissipate without precipitation. This sensitivity to initial conditions, combined with chaotic atmospheric behavior, means forecasts become less reliable as they extend further into the future. Predicting whether it will rain next week involves fundamentally different certainty levels than stating it will rain in an hour based on approaching radar echoes. The 71st mystery explores the beautiful phenomenon of morning dew and why it appears even without rain. Dew forms when surfaces cool below the dew point temperature, causing water vapor to condense directly onto grass, leaves, spiderwebs, and other objects. This process removes moisture from air without any precipitation falling from clouds. Heavy dew can deposit water equivalent to light rain, providing moisture for plants and small animals. The presence of dew on clear nights demonstrates that water cycles between surface and atmosphere constantly, not only during obvious rain events. The 72nd mystery concerns why rain sometimes has a distinctive metallic taste. This sensation typically results from ozone produced by lightning, which can create a taste perception even when present in very small concentrations. The metallic quality may also involve our perception of minerals dissolved in rainwater, or a cross-sensory response to the smell of rain interacting with taste receptors. Our senses of smell and taste intertwine so closely that changes in atmospheric chemistry during rain can create taste impressions, even without anything directly touching our tongues. The 73rd mystery involves the cultural significance rain holds across human societies. Virtually every culture has developed rain-related deities, ceremonies, dances, and folklore, reflecting precipitation's fundamental importance for agriculture and survival. Rain gods appear in mythologies worldwide, from the thunderbirds of Native American traditions to the rain-making powers of Australian Aboriginal songmen. These cultural traditions recognize rain's power to bring both life and destruction, expressing humanity's complex relationship with weather through stories and rituals passed down generations. The 74th mystery explores rain's appearance in art, literature, and music throughout human history. Rain serves as metaphor for sadness, renewal, cleansing, romance, and countless other themes in creative works. The sound of rain inspires composers, while its visual qualities challenge painters attempting to capture falling water on canvas. Writers use rain to set mood, foreshadow events, or symbolize emotional states. This artistic fascination with precipitation demonstrates how deeply rain has embedded itself in human consciousness beyond its practical importance. The 75th mystery concerns why rain sometimes feels romantic, a perception so widespread it appears across cultures and generations. Theories suggest rain's isolating effect creates intimate spaces where people shelter together, fostering connection. The sound and sight of rain might trigger psychological associations with safety, comfort, and slowing down, emotional states conducive to romantic feelings. Petricha's pleasant scent potentially influences mood through pathways connecting olfactory processing with emotional centers in the brain. Whatever the explanation, rain's romantic reputation persists across societies and personal experiences. The 76th mystery involves the strange behavior of rain during extreme cold, when supercooled droplets remain liquid despite temperatures below freezing. Supercooled rain forms when water falls through air cold enough to freeze it, but lacks freezing nuclei, particles that ice crystals need as foundations for formation. These droplets remain liquid until striking surfaces, where they instantly freeze into smooth ice layers. Freezing rain creates hazardous conditions, but also transforms landscapes into crystalline wonderlands, where every surface glitters with ice coating. The 77th mystery explores how climate change is altering global rainfall patterns. As atmosphere warms, it holds more moisture, potentially intensifying precipitation events, while also extending dry periods between rains. Some regions experience increased flooding from more intense downpours, while others face prolonged droughts. These shifts in rain patterns pose challenges for agriculture, water management, and urban planning, requiring societies to adapt to changing precipitation regimes that may differ substantially from historical norms. The 78th mystery concerns rain's role in purifying air by washing out particulate matter and certain gases. This cleansing action improves air quality during and after rainfall, explaining why many people notice breathing feels easier after storms. However, the first rain after dry periods can initially worsen air quality by releasing accumulated pollutants from surfaces, creating a brief period of increased ground-level contamination before subsequent rain continues the cleaning process. The 79th mystery involves the phenomenon of diamond dust, a form of precipitation where tiny ice crystals fall from clear or nearly clear skies. This delicate frozen rain occurs when air temperatures drop extremely low, while humidity remains relatively high, causing ice crystals to form and descend slowly, sparkling like tiny diamonds as they catch sunlight. Diamond dust appears most commonly in polar regions, but can occur anywhere conditions permit, creating an ethereal display that seems magical in its delicacy. The 80th mystery explores how rain affects animal behavior, triggering reproduction, migration, or other activities synchronized with wet seasons. Many species time their life cycles to rainfall patterns, from frogs that emerge to breed when rain fills temporary pools, to birds that begin nesting when increased precipitation promises abundant food supplies. These evolutionary adaptations demonstrate how deeply rain influences entire ecosystems, not just through the water it provides, but through the timing signals it sends to uncounted species. The 81st mystery concerns why walking in rain can feel simultaneously invigorating and calming. The physical sensation of raindrops on skin provides gentle tactile stimulation, while the need to navigate wet conditions demands present-moment attention. Rain sounds and smells trigger relaxation responses, while the mild physical challenge of moving through precipitation increases arousal just enough to enhance alertness without creating stress. This unique combination explains why many people find rain walks strangely satisfying despite getting wet. The 82nd mystery involves the formation of morning fog, which represents a form of cloud formation at ground level. Fog often develops overnight when ground cools through radiation into clear skies, chilling adjacent air below its dew point. Water vapor then condenses into microscopic droplets suspended in air, creating the characteristic reduced visibility of fog. While fog isn't rain, it demonstrates similar principles of condensation and can deposit moisture through direct contact with surfaces, a process called fog drip that provides water in some coastal and mountain regions. The 83rd mystery explores why some storms produce primarily rain, while others generate mostly snow, sleet, or freezing rain. The determining factor involves temperature profiles through atmospheric layers the precipitation falls through. Warm air throughout creates rain, while temperatures below freezing at all levels produce snow. Intermediate scenarios where air temperature varies with altitude create sleet, when falling snow melts then refreezes, or freezing rain, when supercooled droplets freeze on contact with cold surfaces. These temperature variations, often occurring within narrow bands, can create dramatic differences in precipitation type across short distances. The 84th mystery concerns the maximum size of raindrops and why they can't grow indefinitely. As drops increase in diameter, air resistance during their fall causes increasing distortion to their shape. Beyond about 6 millimeters across, drops become so unstable they break apart into smaller droplets. This upper limit helps explain the characteristic size distribution of raindrops, with most falling between 0.5 millimeter and 5 millimeters. The absence of larger drops results not from limits on cloud processes, but from aerodynamic constraints during descent. The 85th mystery involves why rain gauge measurements can vary significantly across short distances. Local topography, building effects, and wind patterns all influence how much rain reaches collection surfaces. Rain falling with strong winds may blow past gauges while accumulating on vertical surfaces, explaining why manual measurements sometimes show more rain than automatic gauges recorded. These variations demonstrate that asking how much it rained requires specifying location precisely, as amounts can differ substantially within a single neighborhood. The 86th mystery explores the phenomenon of mammatus clouds, distinctive pouch-like formations that sometimes appear after thunderstorms. These striking clouds form when cold, sinking air creates bulges that descend from the cloud base, creating a bumpy appearance reminiscent of a quilted blanket or array of pouches. While often associated with severe weather, mammatus clouds themselves don't produce rain or indicate immediate danger. Their appearance signals complex atmospheric conditions that produce the preceding storms. The 87th mystery concerns why rain intensity varies so dramatically between gentle drizzle and torrential downpours. These differences reflect variations in cloud updraft strength, droplet size distribution, and atmospheric moisture content. Light drizzle produces perhaps 1 millimeter of accumulation per hour from clouds with weak updrafts and small droplets. Cloudburst downpours can dump over 100 millimeters per hour when strong updrafts and abundant moisture create large drops falling in dense concentrations. The difference between these extremes illustrates precipitation's dynamic range. The 88th mystery involves the formation of rain bands in tropical cyclones, curved structures that spiral outward from the storm center. These bands develop where converging winds force air upward, creating zones of enhanced precipitation separated by regions of lighter rain or no rain. Rain bands can extend hundreds of kilometers from a cyclone's center, bringing heavy rainfall and gusty winds to areas far from the eye. Understanding rain band structure helps forecasters predict which areas will experience the heaviest precipitation as tropical systems approach. The 89th mystery explores why rain sometimes produces a distinct smell on hot pavement that differs from the earthy petrichor of rain on soil. This urban rain scent results from rainfall releasing accumulated oils, rubber residues, and other materials that accumulate on pavement during dry periods. The heated surfaces volatilize these compounds, creating a distinctive aroma that mixes with or replaces petrichor, depending on the local surface composition. This urban variation of rain's smell demonstrates how human environments alter even this fundamental natural experience. The 90th mystery concerns the role rain plays in Earth's electrical circuit, completing connections between thunderstorm generators and ground. Thunderstorms act like batteries, creating charge separation that drives currents through atmosphere. Rain provides conductive paths that allow charge to flow back to Earth, maintaining the planet's electrical balance. This continuous process, occurring simultaneously in thousands of thunderstorms worldwide, keeps Earth's fair weather electric field relatively constant despite constantly operating lightning discharges. The 91st mystery involves why rain sometimes appears to have different colors when viewed against various backgrounds. While raindrops themselves remain colorless, the light they scatter or transmit depends on viewing angle, illumination conditions, and background colors. Rain falling against dark storm clouds might appear gray or white from scattered light, while the same rain viewed against a bright background could seem nearly invisible. These variations result from rain's optical properties and demonstrate how our perception depends on context as much as the rain itself. The 92nd mystery explores the concept of rain streaks, the patterns created by falling droplets that our eyes perceive as continuous lines rather than separate drops. This visual effect results from motion blur and persistence of vision, the same phenomena that make movies appear to show continuous motion despite consisting of individual still frames. Rain streaks appear longer and more pronounced during heavy rain, when higher drop concentrations and faster fall speeds create overlapping visual trails that merge into the characteristic appearance of sheeting rain. The 93rd mystery concerns why some people claim to feel rain approaching through aching joints or old injuries. While scientific evidence remains debated, proposed mechanisms include responses to changing barometric pressure, which drops before many rainstorms. Pressure changes might affect fluid-filled spaces in joints or influence how nerves transmit pain signals. Whether these responses can reliably predict rain remains uncertain, but the widespread nature of such reports suggests some connection between weather changes and physiological sensations exists, even if mechanisms remain incompletely understood. The 94th mystery involves the formation of those beautiful temporary waterfalls that appear during heavy rain, tumbling over rocks and ledges that remain dry most of the year. These ephemeral flows demonstrate water's ability to quickly concentrate and create dramatic features that vanish almost as suddenly as they appeared. Some waterfalls might flow only hours after each rain before disappearing until the next storm, existing in that liminal space between permanent landscape features and completely temporary phenomena. The 95th mystery explores why rain sounds different when heard from indoors versus being outside in the downpour. Indoor listening provides acoustic filtering through building materials, often emphasizing lower frequencies while dampening highs, creating a more muffled, bass-heavy sound. Outside, you hear the full frequency range plus subtle sounds of individual drops striking various nearby surfaces. Wind noise, water running off surfaces, and splashing from puddles add layers to the outdoor rain soundscape that indoor listening misses, making the two experiences acoustically distinct. The 96th mystery concerns the psychological phenomenon of rain memory, why certain rains can trigger vivid recollections of specific past events or periods. Rain engages multiple senses simultaneously: sight, sound, smell, tactile sensation, and sometimes taste, creating rich memory associations. The distinctive character of rain's sensory profile makes it an effective memory cue, where catching petrichor or hearing specific rain sounds can transport consciousness decades into the past, bringing forgotten memories suddenly back to awareness with surprising clarity and emotional immediacy. The 97th mystery involves why rain can make some people feel melancholic or introspective. Theories suggest reduced light during rainy weather influences mood through effects on circadian rhythms and neurotransmitter production. Rain sound creates an auditory environment that encourages inward focus rather than external engagement. The enforced slowdown of rain-limited activities might provide space for reflection that busy schedules normally prevent. These factors combine to create the pensive, sometimes wistful quality many associate with rainy days. The 98th mystery explores the connection between rain and creativity, with many people reporting enhanced creative thinking during rainfall. Explanations include rain's masking of distracting noises, creating optimal conditions for focus and imagination. The white noise effect might also reduce overactive mental filtering, allowing more associations and connections to form. Rain's calming influence could reduce stress that inhibits creative thinking. Whatever the mechanism, enough people experience this effect that rainy day creativity has become a recognized phenomenon worthy of scientific investigation. The 99th mystery concerns why rain cessation sometimes feels as noticeable as its beginning. The sudden awareness that rain has stopped even when you weren't consciously listening. This perception demonstrates how our brains continuously monitor environmental sounds, even when attention focuses elsewhere. The absence of rain's acoustic signature registers as a change significant enough to draw attention back to auditory processing. This sensitivity to environmental change helped our ancestors detect approaching threats and opportunities, remaining relevant even in modern settings, where rain stopping rarely signals immediate danger. The 100th and final mystery involves the simple magic of watching rain fall, an activity that has captivated humans throughout history. Whether observing from windows, shelters, or while accepting soaking, there's something fundamentally mesmerizing about watching water return from sky to earth. Perhaps this fascination reflects our recognition of rain's vital importance, or maybe it taps into something more primal, the endless cycling of water that has sustained life on Earth for billions of years, continuing unchanged while everything else around it transforms. As we reach the end of tonight's journey through rain's mysteries, We've traveled from microscopic cloud droplets to global weather patterns, from ancient bacteria producing petrichor to the modern science explaining rain's many effects on our bodies and minds. We've explored strange rains of fish and colored water, learned why rain sounds soothe us into sleep, and discovered how rainfall shapes everything from landscapes to cultures. Rain continues falling tonight somewhere on Earth, as it has every day since our planet's atmosphere stabilized billions of years ago. Those same cycles of evaporation and precipitation keep turning, driven by solar energy and governed by physical principles that operate with patient consistency. The mysteries we've explored tonight represent just a fraction of what remains to be discovered about this familiar, yet endlessly complex phenomenon. As rain falls outside your window, or even if skies remain clear where you rest tonight, perhaps you'll find yourself listening a bit more carefully next time precipitation arrives, noticing the subtle variations in sound, or pausing to appreciate that distinctive scent rising from wet earth. Rain connects us to processes larger and older than human civilization, yet its mysteries touch each of us personally through memories, sensations, and the simple wonder of water falling from the sky. Rest well tonight, knowing that whether rain falls or not, the great cycles continue, water evaporating into air, forming clouds, and eventually returning to Earth in countless drops, each one a small mystery, contributing to the larger mysteries we've explored together. May your dreams be peaceful, and may the gentle mysteries of rainfall carry you into deep, restorative sleep. Tonight's journey through rainfall's mysteries continues as we drift deeper into the phenomena that make rain such an endlessly fascinating presence in our world. Beyond the 100 mysteries we've already explored, rain holds countless more secrets waiting to be discovered in the spaces between raindrops, in the silence after storms, and in the patient cycles that have operated since water first fell on this planet. The mystery of rain's temperature reveals fascinating patterns about atmospheric conditions. Rain falling through warm air can arrive at surface temperatures ranging from cool to almost tepid, while winter rain descends through cold layers that chill droplets to just above freezing. This temperature variation affects not only how rain feels on skin, but also influences its behavior on surfaces, determining whether it evaporates quickly or lingers, whether it creates mist or simply soaks into waiting ground. The thermodynamics of falling raindrops create their own microclimate, a column of cooling air surrounding each descending sphere. Another mystery involves how different surfaces respond to rain's arrival. Concrete and asphalt darken when wet as water fills microscopic pores and changes how light reflects and absorbs. Wood can swell as it absorbs moisture, sometimes causing doors to stick or boards to warp. Metal surfaces cool rapidly as rain's evaporation draws heat away. These varied responses demonstrate rain's active interaction with materials, not simply wetting them, but changing their properties temporarily, or, with sufficient time and repeated exposure, permanently altering their character. The mystery of rain's role in plant life extends beyond simply providing moisture. Rainfall delivers dissolved minerals and nutrients from atmosphere to soil, sometimes transporting these materials thousands of miles from their sources. Rain also physically interacts with foliage, washing dust and debris from leaves to improve photosynthetic efficiency. The mechanical action of raindrops can trigger certain plants to release spores or pollen, timing reproduction to coincide with conditions favorable for dispersal. Some species have evolved leaves that channel water to roots efficiently, creating natural irrigation systems that maximize benefit from each rainfall event. Rain's influence on soil chemistry presents another intriguing mystery. When rain percolates through soil layers, it dissolves and transports minerals, organic compounds, and microorganisms to different depths. This leaching process helps distribute nutrients while also potentially removing beneficial materials beyond reach of plant roots. The pH of rain influences how quickly certain minerals dissolve and become available to living organisms. Over long periods, rainfall patterns literally shape the chemical composition of entire landscapes, determining which minerals accumulate where, and consequently, which plants can thrive in different locations. The mystery of how rain sounds change with intensity and drop size creates a rich acoustic landscape. Light drizzle produces a soft, almost whispering patter, while moderate rain generates a steady drumming rhythm. Heavy downpours create an almost roaring sound as countless large drops pound surfaces simultaneously. Each intensity level corresponds to different drop sizes and fall rates, creating distinct sonic signatures that experienced listeners can interpret to estimate rainfall, amount, and duration. These acoustic variations help explain why rain sounds recorded for relaxation come in so many varieties, each creating a slightly different emotional response. Another fascinating mystery involves rain shadows cast not by mountains, but by large buildings and other structures. Tall buildings can deflect wind patterns, creating zones immediately downwind, where less rain falls than surrounding areas receive. This urban rain shadow effect contributes to the complex mosaic of microclimates within cities, where precipitation amounts can vary significantly across neighborhoods due to building arrangements and heights. Trees create similar but smaller scale rain shadows, sheltering areas beneath their canopies while channeling more water to fall along the outer edges of their foliage. The mystery of rain's electrical properties extends beyond lightning to include the normal electrical state of raindrops. Each drop carries a slight electrical charge acquired through friction with air molecules during descent. These charges, though individually tiny, collectively contribute to atmospheric electricity and influence how raindrops interact with surfaces and each other. The polarity and magnitude of these charges can affect how efficiently rain washes out air pollution and how drops coalesce or bounce apart when they collide. Rain's influence on groundwater recharge presents mysteries about timing and pathways. Not all rain that falls immediately enters underground aquifers. Some evaporates, some runs off into streams, and some is absorbed by vegetation. The portion that does infiltrate must navigate complex networks of soil pores and rock fractures. A journey that might take days, months, or even years, depending on geology. Understanding these pathways and timing helps explain why some wells respond quickly to rainfall, while others show delayed responses, and why protecting recharge areas proves so crucial for groundwater sustainability. The mystery of rain's psychological effects on groups and societies reveals fascinating patterns. Rainy weather tends to reduce crime rates, with violent incidents particularly declining during precipitation. Theories suggest rain keeps potential troublemakers indoors, reduces foot traffic that provides opportunities for certain crimes, and generally dampens the social activity that can lead to conflicts. Rain also influences consumer behavior, affecting what people buy and when they shop. Restaurants may see decreased walk-in traffic, but increased delivery orders. These societal effects demonstrate how weather patterns influence human behavior in subtle but measurable ways. Another mystery involves how rain triggers specific memories through scent associations. The smell of rain might evoke a particular summer, a specific location, or an emotional state from years past. This phenomenon results from how olfactory processing connects directly to brain regions involved in emotion and memory, creating unusually powerful associations between smells and past experiences. Rain's distinctive scent becomes linked with whatever occurred during previous encounters with that smell, explaining why petrichor can transport some people instantly to childhood summers or remind others of romances from decades past. The mystery of how animals predict rain has fascinated humans for centuries. Certain behaviors, such as cows lying down, ants marching in lines toward higher ground, or birds flying low, have been interpreted as rain omens. While scientific verification of these behaviors remains incomplete, some may have bases in animals detecting barometric pressure changes, increased humidity, or other atmospheric shifts that often precede rainfall. These sensitivities, if real, would represent remarkable evolutionary adaptations that provided survival advantages to creatures able to seek shelter or adjust behavior before storms arrived. Rain's role in spreading plant diseases and pathogens creates mysteries about infection patterns and timing. Splash dispersal occurs when raindrops strike soil or infected plant material, creating tiny droplets that carry fungi, bacteria, or viruses to new hosts. Heavy rain can spread disease through entire crop fields in hours, making rainfall timing and intensity crucial factors in agricultural disease management. Understanding these dispersal mechanisms helps explain why certain plant diseases appear epidemic in wet years but nearly absent during droughts. The mystery of freezing rain's formation requires such precise atmospheric conditions that it remains relatively rare despite being so dangerous. A layer of warm air must exist above freezing air at the surface, with rain falling from cold clouds above the warm layer. Drops melt partially or completely in the warm layer, then become supercooled as they fall into surface-level cold air. This temperature inversion creates a narrow zone where freezing rain occurs, often just a few miles wide, explaining why ice storms typically affect limited areas while causing tremendous damage within those zones. Another mystery involves the maximum rainfall possible in a given period. Theoretical limits exist based on atmospheric moisture capacity and updraft strength needed to sustain rain production. The record for most rain in 1 minute stands at just over 1 inch, while the 24-hour record exceeds 70 inches. These extreme events require extraordinary conditions where all factors align to produce catastrophic rainfall rates. Understanding these limits helps engineers design infrastructure to withstand probable maximum precipitation events, though climate change may be shifting what constitutes maximum possible rainfall in some regions. The mystery of rain's interaction with snow creates the complex weather known as wintry mix, where precipitation type constantly shifts. Temperature profiles through the atmosphere determine whether snow reaches the surface intact, partially melts into sleet, or fully melts to become rain. These transitions occur over narrow temperature ranges, often resulting in weather that alternates between types within minutes or varies dramatically across short distances. The slush and ice that result from mixed precipitation create especially hazardous conditions precisely because their properties remain less predictable than pure rain or snow. Rain's aesthetic qualities have inspired artists throughout human history, yet capturing its visual essence remains challenging. Painters must suggest motion, transparency, and the complex lighting effects rain creates, without being able to literally show individual drops at realistic scales. Photographers face similar challenges, needing fast shutter speeds to freeze droplets or slow speeds to create motion blur that suggests rainfall's dynamic quality. These artistic challenges reflect rain's fundamentally ephemeral nature, present one moment and gone the next, existing as process rather than stable object. The mystery of how rain affects human circadian rhythms involves the reduction in light levels during stormy weather. Darker daytime conditions can confuse internal biological clocks that rely on light intensity to maintain proper timing. This confusion might contribute to the sleepiness many people feel during rainy days, as their bodies interpret reduced light as a signal that evening approaches. Over extended periods, persistent cloudy weather can affect mood and energy levels through these disruptions to circadian timing, explaining why some people struggle more with rainy seasons than others. Another mystery concerns how rain influences sound propagation beyond simply masking noise. Rain changes acoustic properties of air by increasing humidity and introducing sound-absorbing surfaces as water accumulates on vegetation and structures. These effects alter how fast sounds travel and how clearly they can be heard, with some frequencies affected more than others. The result creates a soundscape distinctly different from dry weather conditions, influencing everything from how we perceive distances to how wildlife communication functions during rainfall. The mystery of rain's role in nutrient cycling reveals its importance beyond simple water delivery. Rainfall helps transport nitrogen fixed by lightning or industrial processes from atmosphere to soil where plants can use it. Rain washes nutrients from leaves and bark, creating through-fall and stem flow enriched with minerals that nourish soil organisms and plant roots. This nutrient redistribution facilitated by rain represents a crucial ecosystem service that connects atmospheric, vegetation, and soil systems in continuous cycles of resource movement. Rain's effect on air pressure patterns creates mysteries about storm development and movement. Evaporating rain cools surrounding air, increasing its density and causing it to sink. This descending air spreads outward at the surface, potentially triggering new cloud formation and precipitation, where it encounters warm, moist air. These rain-cooled outflows can propagate storms across landscapes, explaining how isolated showers sometimes evolve into organized systems that persist for hours, despite individual cells lasting only briefly. The mystery of rain gauge sighting illustrates how measurement location profoundly affects recorded values. Gauges positioned too close to buildings or trees receive less rain due to shelter effects. Those placed too high above ground may miss precipitation that falls at surface level. Windshields around gauges help minimize errors caused by turbulence that deflects drops away from collection openings. Despite standardization efforts, rain measurements remain somewhat uncertain, with the value recorded depending on precisely where and how the gauge sits within the landscape. Another mystery involves double rainbows and the even rarer, higher-order rainbows that can occasionally form. Triple and quadruple rainbows require specific conditions, where sunlight undergoes 3 or 4 internal reflections within raindrops before exiting. These higher-order bows appear much fainter than primary and secondary rainbows, and often go unnoticed unless observers know to look for them. The mathematical beauty of rainbow formation extends to these rare phenomena, demonstrating how simple principles of light refraction and reflection combine to create increasingly complex optical displays. Rain's role in pollination might seem limited compared to wind or insect pollination, but some plants exploit rainfall for reproduction. Rain splash can carry pollen from male to female flower parts in certain species. Other plants release pollen only when rain wets specialized structures, timing reproduction to ensure seeds develop during wet periods favorable for germination. These rain-mediated pollination strategies, though less common than other mechanisms, demonstrate nature's ability to utilize every available resource, including the mechanical energy of falling raindrops. The mystery of how clouds determine when to release rain involves complex interactions between updrafts, droplet size, and atmospheric stability. Clouds can hold precipitation for extended periods if conditions support continued suspension, only releasing rain when updrafts weaken or drops grow large enough to overcome vertical air currents. This threshold behavior means cloud appearance doesn't always indicate imminent rainfall, with some impressive-looking clouds producing little or no precipitation, while smaller clouds occasionally generate surprising amounts of rain. Rain's influence on atmospheric visibility extends beyond the obvious blurring of distant objects. Heavy rain increases light scattering, effectively reducing the distance at which objects remain visible. This effect, combined with windshield refraction and the need for wipers that temporarily obstruct vision, explains why driving in rain proves more challenging than driving in clear conditions even on well-lit roads. The reduced visibility affects not just human perception, but also automated systems that rely on optical sensors, creating challenges for technologies from security cameras to autonomous vehicles. Another mystery involves the formation of steam or mist rising from pavement during summer rain. This visible vapor forms when rain's evaporative cooling creates temperature differences between cool droplets and hot surfaces. Water vaporizes rapidly from the superheated pavement, creating local humidity spikes that condense into visible fog. This dancing mist, particularly common during first rain after extended dry periods, creates ethereal visual effects that transform familiar streets into mysterious landscapes wrapped in ground-hugging clouds. The mystery of how rain affects electromagnetic wave propagation influences technology from radio to satellite communications. Water droplets absorb and scatter radio waves, with attenuation increasing at higher frequencies. Heavy rain can degrade satellite signals, disrupt terrestrial microwave links, and affect radar performance. These impacts vary with rain intensity, drop size distribution, and transmission frequency, creating complex relationships between weather and communication system reliability. Engineers must account for rain effects when designing wireless systems, particularly for critical applications requiring consistent performance regardless of weather. Rain's connection to seasonal affective patterns reveals mysteries about mood regulation and light exposure. Extended rainy seasons, particularly at high latitudes where they coincide with short days, can trigger depression in susceptible individuals. The reduced sunlight during cloudy weather decreases vitamin D production and affects neurotransmitter levels, potentially contributing to mood changes. However, some people find rainy weather energizing or comforting, demonstrating that psychological responses to precipitation vary widely based on individual differences and cultural context. The mystery of how rain gardens work reveals elegant solutions for managing stormwater runoff. These landscape depressions collect and infiltrate rainwater, allowing it to soak into ground rather than flowing directly into storm drains. Native plants in rain gardens tolerate both flooding during rain and drought between storms, while their roots create channels that enhance water infiltration. This nature-based approach to drainage demonstrates how understanding rain's behavior enables designs that work with natural processes rather than against them. Another mystery concerns how different musical instruments attempt to recreate rain sounds. Rain sticks use seeds or beads cascading through internal baffles to simulate rainfall's acoustic character. Electronic musicians layer random percussion sounds to approximate rain's complexity. Despite these efforts, natural rain remains difficult to duplicate convincingly, perhaps because its sound contains subtle variations and organic qualities that resist systematic reproduction. The challenge of artificial rain sounds highlights the remarkable richness present in this seemingly simple natural phenomenon. Rain's effect on traffic patterns creates mysteries about how precipitation influences human movement and decision-making. Even light rain reduces traffic speeds as drivers adjust for wet conditions. Heavy rain can dramatically alter commuting patterns as people delay trips or choose alternative routes. These behavioral changes cascade through transportation networks, sometimes causing congestion in unexpected locations. Understanding these rain-induced traffic effects helps planners anticipate problems and potentially mitigate them through better infrastructure design or intelligent traffic management systems. The mystery of rain's thermal effects on buildings involves complex heat transfer processes. Summer rain cools building exteriors through evaporation, potentially reducing air conditioning needs. Winter rain, conversely, can carry heat away from buildings faster than dry air, increasing heating requirements. These effects depend on building materials, insulation levels, and local climate characteristics, creating microclimate variations that affect energy use. Architects increasingly consider rain's thermal impacts when designing structures for specific climates. Rain's role in creating natural sounds beyond its own patter presents interesting mysteries. Rain swells rivers and streams, creating background soundscapes of flowing water that persist after precipitation ceases. Runoff trickling through leaf litter produces delicate musical notes. Water dripping from branches creates irregular rhythms that vary with wind and remaining water quantity. These rain-generated sounds contribute to the acoustic richness of natural environments, providing layers of audio that change throughout and after precipitation events. Another mystery involves how rain influences human olfactory experience beyond petrichor. Rain releases terpenes from pine needles, creating that distinctive evergreen scent. It volatilizes oils from eucalyptus and other aromatic plants. Rain on dry sage or chaparral produces characteristic scents immediately recognizable to anyone familiar with arid region vegetation. These plant-derived aromas combine with petrichor to create location-specific rain smells that vary by ecosystem and season, making each rain's scent profile unique. The mystery of rain's appearance in religious and spiritual traditions spans cultures worldwide. Rain often symbolizes divine blessing, cleansing, or renewal. Many religions include rain-related prayers, ceremonies, or deities. This spiritual significance reflects rain's fundamental importance for agriculture and survival throughout human history. Even in modern societies with sophisticated water infrastructure, rain retains symbolic power that connects contemporary life to humanity's agricultural heritage and dependence on weather patterns. Rain's interaction with artificial lighting creates mysteries about perception and visual phenomena. Streetlights during rain produce halos and streaks as light refracts through drops. Headlights illuminate falling rain, making individual drops visible as streaking lines in the beam. These lighting effects transform rain from nearly invisible to dramatically apparent, depending on illumination angle and intensity. The visual change illustrates how context profoundly affects how we perceive rain, with the same precipitation appearing completely different under various lighting conditions. The mystery of rain prediction in folklore involves generations of accumulated weather wisdom. Sayings like "red sky at night" suggests rain timing based on observations of cloud and light conditions. Animal behavior omens, such as frogs singing predicting rain, contain kernels of truth mixed with superstition. While modern meteorology surpasses folk methods in accuracy, traditional rain lore demonstrates humanity's long history of attempting to understand and forecast precipitation patterns crucial for survival. Another mystery concerns how rain supports entire ecosystems in rainforests, where precipitation exceeds 80 inches annually. The constant moisture enables incredible biodiversity, supporting more species per acre than any other terrestrial ecosystem. Rainforest plants and animals have evolved remarkable adaptations to wet conditions, from water-shedding leaves to amphibians that complete their entire life cycles in tree canopy pools of accumulated rainwater. These ecosystems demonstrate what becomes possible when rain falls abundantly and reliably. The mystery of how rain affects insect populations reveals complex ecological relationships. Heavy rain can knock flying insects from the air, temporarily reducing their numbers. Conversely, rain fills temporary pools where mosquitoes and other aquatic insect larvae develop, potentially causing population booms. Certain insects emerge only after rain, synchronizing life cycles with moisture availability. These rain-mediated population dynamics cascade through food webs, affecting birds, bats, and other insectivores that depend on bugs for sustenance. Rain's role in shaping cultural practices extends to architecture, with building designs reflecting local rainfall patterns. Steep roofs in wet climates shed water efficiently. Desert structures often feature flat roofs since rain rarely falls. Roof overhangs, gutters and drainage systems all respond to precipitation characteristics of their locations. These architectural adaptations demonstrate how rain influences human creativity and engineering, with each climate's rainfall pattern requiring specific design solutions. The mystery of how rain begins breaking down rock through chemical weathering occurs gradually over geological time. Rain's natural acidity, enhanced in some cases by air pollution, slowly dissolves minerals from rock surfaces. This dissolution creates soil, releases nutrients, and gradually shapes landforms. While individual drops achieve almost nothing, billions of drops over thousands of years carve valleys, round mountains, and transform solid stone into fertile earth. This patient but inexorable process demonstrates rain's power when accumulation of tiny effects occurs across vast timescales. Another mystery involves the formation of rain circles that appear when drops strike standing water. Each impact creates expanding ripples that interfere with neighboring circles in complex patterns. These ephemeral geometric displays last only moments before new drops create fresh patterns, generating an ever-changing kaleidoscope of interference waves. The mathematical beauty underlying these patterns connects simple physics to complex emergent behaviors, turning rain puddles into demonstrations of wave mechanics and pattern formation. Rain's influence on river levels and flooding creates mysteries about how watersheds respond to precipitation. Some rivers rise and fall rapidly after rain, while others show delayed responses. These differences reflect basin size, soil permeability, vegetation cover, and topography. Understanding these relationships helps predict flooding risk and manage water resources. However, human alterations to landscapes can change how watersheds respond to rain, sometimes creating flood risks where none previously existed. The mystery of rain sounds penetrating dreams and influencing their content has been noted by many but studied by few. Anecdotal reports describe dreams featuring water, beaches, or storms when rain falls during sleep. These incorporations suggest that sleeping minds continue processing environmental sounds, weaving them into dream narratives. The phenomenon demonstrates how permeable the boundary between external experience and internal mental states remains even during sleep. Rain's role in cultural metaphors and language reveals how deeply precipitation has embedded itself in human thought. We speak of raining ideas, weathering storms of criticism, or feeling under the weather. These linguistic patterns demonstrate rain's pervasiveness as a source of imagery for describing non-meteorological experiences. The ubiquity of rain metaphors across languages suggests that weather patterns profoundly shaped how human cognition developed frameworks for understanding abstract concepts. Another mystery concerns how rain interacts with spider webs, making these normally nearly invisible structures suddenly apparent. Water droplets cling to silk strands, outlining web architecture in jewelry-like displays. This enhanced visibility comes at a cost for spiders, as weighted webs lose their structural integrity and become less effective traps. Some spiders respond by taking down webs during rain and reconstructing them afterward, demonstrating behavioral adaptations to precipitation's effects on their hunting tools. The mystery of how frozen rain affects power lines creates hazards beyond simple weight loading. Ice accumulation increases wind resistance, making lines more susceptible to damage from gusts that normally wouldn't cause problems. Ice can also bridge the gap between power lines and nearby branches, creating short circuits. The combined effects of weight, wind, and electrical hazards make ice storms particularly destructive to utility infrastructure, sometimes leaving regions without power for extended periods. Rain's contribution to groundwater contamination presents mysteries about pollutant transport through soil. Rain carries surface contamination deeper into soil profiles, potentially threatening aquifers. The same infiltration processes that recharge groundwater can also introduce pesticides, fertilizers, or other pollutants into underground systems. Understanding these transport mechanisms proves crucial for protecting drinking water sources from contamination originating at the surface. The mystery of why some clouds produce virga while nearby clouds generate substantial rainfall involves subtle differences in atmospheric moisture profiles. Clouds over drier air masses produce virga as falling rain evaporates completely. Adjacent clouds over moister air might generate precipitation that reaches ground. These moisture variations can exist across remarkably short distances, explaining how one observer experiences rain while someone a few miles away sees only virga streaking from cloud bases. Another mystery involves rain's cooling effect on urban heat islands, temporary but significant reductions in temperature that occur during and after precipitation. Evaporating rain draws heat from surfaces and air, potentially lowering temperatures by several degrees. This cooling provides temporary relief during summer heat waves, though the effect proves short-lived once rain ceases and surfaces dry. Understanding urban rain cooling helps predict how much temperature relief precipitation might provide during extreme heat events. Rain's acoustic signature variations with geography create location-specific soundscapes. Tropical rains often feature larger drops, producing deeper sounds than temperate precipitation. Desert rain, when it occurs, might sound different due to hard surfaces and sparse vegetation affecting how sounds reflect. These geographic variations mean that rain sounds recorded in one location may not perfectly match another's rain character, explaining why some sleepers prefer recordings from specific regions or climate zones. The mystery of how rain affects air quality immediately after precipitation reveals complex patterns. While rain generally cleanses air, the first period of rainfall after a dry spell can temporarily worsen air quality as accumulated pollutants are washed from surfaces and stirred into the air. Only after continued rain does the overall cleansing effect dominate, improving breathing conditions. This temporal pattern affects when spending time outdoors during rain might prove most beneficial for respiratory health. Rain's role in seed dispersal for certain plant species demonstrates evolutionary adaptations to utilize falling water. Rain splash can propel seeds several feet from parent plants, while rainwater flowing across ground can carry seeds considerable distances. Some seed coats are designed to swell or soften only when thoroughly soaked, ensuring germination occurs when soil moisture should be adequate. These rain-mediated dispersal mechanisms complement wind and animal transport methods. Another mystery involves measuring rain from space using satellites equipped with specialized sensors. Radar and microwave instruments can detect precipitation within clouds and estimate rainfall rates across large areas. This remote sensing provides coverage over oceans and remote regions where ground stations don't exist. However, satellite rain measurements require careful calibration and validation using ground truth data, as estimating rainfall amounts from space involves complexities that continue challenging scientists. The mystery of rain's influence on ocean surface conditions extends beyond the obvious addition of fresh water. Heavy rain can temporarily lower salinity in surface layers, affecting density and potentially influencing current patterns. Rain creates distinctive patterns on ocean surfaces, visible from ships or aircraft, as areas of reduced wave activity where raindrops dampen capillary waves. These subtle effects demonstrate how rain interacts with marine environments in ways beyond simply transferring water from atmosphere to ocean. As this extended exploration of rain's mysteries draws toward its conclusion, we've journeyed through phenomena spanning molecular chemistry to global climate patterns, from individual human perceptions to ecosystem-level processes. Rain emerges from these investigations not as a simple weather event, but as a complex phenomenon touching every aspect of life on Earth, influencing our planet's systems in ways both obvious and subtle, direct and indirect. The mysteries we've explored tonight demonstrate that familiarity doesn't diminish wonder. Despite experiencing rain throughout our lives, despite scientific understanding of its mechanisms, precipitation retains power to surprise, soothe, and inspire. Each rainfall represents a unique event, never exactly duplicated in its particular pattern of drop sizes, timing, intensity variations, and atmospheric conditions. This endless variety within fundamental similarity creates rain's paradoxical character, utterly familiar, yet perpetually fresh. Perhaps rain's deepest mystery involves its psychological resonance with human consciousness. Beyond practical importance for agriculture and ecology, beyond the measurable physical effects, rain speaks to something in human nature that responds to its arrival with feelings ranging from peaceful contentment to melancholic introspection, from joyful celebration to quiet contemplation. This emotional dimension transcends scientific explanation while remaining universally recognized across cultures and individuals. Tonight, whether rain falls outside your window or skies remain clear, may your rest be deep and peaceful. The great atmospheric cycles continue their patient work, water evaporating, condensing, and falling as they have for billions of years. Somewhere on Earth, rain is falling at this very moment, nourishing ecosystems, filling streams, and providing the fresh water that makes life possible. These processes continue regardless of whether we notice them, operating with reliable consistency that grounds the more chaotic aspects of weather and climate. As you drift towards sleep, perhaps the knowledge of these mysteries creates a deeper appreciation for the next time rain taps at your window. Every drop that falls carries within it the history of its journey through atmosphere and the potential for countless future cycles through the water systems of our planet. Every rain shower represents both ending and beginning, water returning to Earth while simultaneously beginning its next ascent through evaporation. May the gentle mysteries of rainfall accompany you into restful sleep, and may you wake refreshed, carrying with you a deeper awareness of the elegant complexity present in this most familiar yet endlessly fascinating natural phenomenon. The rain falls, has fallen, will fall again, connecting past to future through the eternal present of water's cycle. Rest well and dream peacefully under rain's gentle mysteries. The mystery of rain's rhythm and its effect on human movement patterns reveals fascinating connections between weather and behavior. Walking in rain requires different cadences than walking in dry weather as we navigate puddles, adjust stride to avoid splashing, and sometimes alter pace to reach shelter quickly or slow down to enjoy the experience. These movement changes, subtle as they may be, demonstrate how rain influences even our most basic physical interactions with the world. Rain's role in creating temporary habitats for specialized organisms presents ecological mysteries worth exploring. Vernal pools that form during rainy seasons support species found nowhere else, creatures adapted to breed and develop rapidly before their aquatic homes evaporate. Some fairy shrimp species can complete entire life cycles in mere weeks, laying drought-resistant eggs that wait years for the next suitable rain. These specialized adaptations demonstrate evolution's creativity in exploiting ephemeral resources. Another mystery involves how rain affects the behavior of pets and domesticated animals. Dogs may refuse walks during heavy rain, or conversely become excited by precipitation. Cats typically avoid getting wet, though individual preferences vary. Farm animals often seek shelter before rain arrives, possibly detecting atmospheric pressure changes or other meteorological cues. These behavioral variations reflect both instinctual responses and learned associations with rain developed through individual experience. The mystery of rain's influence on sleep architecture, the patterns of sleep stages throughout the night, remains incompletely understood. Anecdotal evidence suggests some people experience deeper or more continuous sleep during rainy nights. Proposed mechanisms include rain sounds masking disrupting noises, the soothing acoustic environment reducing the time to fall asleep, or perhaps even subtle effects of atmospheric pressure changes on physiology. Rigorous scientific studies of these effects remain limited, leaving many questions unanswered. Rain's contribution to shaping regional dialects and vocabulary demonstrates linguistic diversity emerging from environmental differences. Regions with frequent rain develop rich vocabularies for describing precipitation types, from Scott's multiple words for different drizzle intensities to Pacific Northwest residents' nuanced rain terminology. These linguistic patterns reflect cultural adaptations to local climate, where precise communication about rain characteristics holds practical importance for daily life and traditional livelihoods. The mystery of how rain affects wireless sensor networks and Internet of Things devices creates engineering challenges for outdoor technology deployment. Rain can interfere with radio communications between sensors, short-circuit exposed electronics, and create false readings from instruments affected by moisture. Designing weather-resistant systems that maintain functionality during storms requires careful engineering and often represents significant technical challenges, particularly for devices powered by solar panels that also must cope with reduced light during cloudy weather. Rain's role in traditional weather forecasting systems used by indigenous peoples worldwide represents accumulated knowledge refined over generations. Observable signs like cloud formations, wind shifts, animal behaviors, and plant responses were integrated into sophisticated predictive models that often matched or exceeded accuracy of early scientific meteorology. These traditional systems, though lacking technological tools, demonstrated keen observation and pattern recognition applied to understanding local rainfall patterns. Another mystery concerns how rain sounds differ when falling on various roof materials, creating distinct acoustic signatures. Metal roofs produce sharp, ringing tones as drops strike hard surfaces. Tile roofs create deeper, more muted sounds. Thatched roofs nearly silence rain with their thick, absorbent layers. These acoustic variations mean that the subjective experience of rain indoors depends partly on building construction, with some materials creating more soothing soundscapes than others. The mystery of rain's effects on astronomical observations involves both the obvious problem of cloud cover and subtler issues of atmospheric moisture. Even after rain ceases, elevated humidity can reduce visibility and create haze that degrades telescope performance. Professional observatories locate in arid regions partly to avoid these problems, seeking sites where clear, dry skies prevail. Amateur astronomers learn to anticipate how local rain patterns affect their observing opportunities throughout the year. Rain's interaction with light pollution in cities creates unique atmospheric phenomena. Water droplets scatter artificial light, creating glows and halos around streetlights and illuminated buildings. This scattering can actually increase overall sky brightness during rain, making stargazing particularly difficult in urban areas during precipitation. The effect demonstrates how human alterations of the environment interact with natural processes to create conditions unlike those in unmodified landscapes. The mystery of how different cultures celebrate rain after droughts reveals universal recognition of precipitation's importance. Rain dances, prayers for rain, and celebrations when rain arrives appear across societies worldwide. These traditions acknowledge rain's life-giving properties while providing community activities that strengthen social bonds during climatically challenging times. Even in modern societies with sophisticated water infrastructure, the arrival of rain after extended dry periods often brings collective relief and celebration. Another mystery involves rain's effects on outdoor sound propagation and how this influences human activities. Rain generally dampens sound transmission, both through absorption by water droplets and by creating masking noise. This acoustic environment affects everything from wildlife communication to human conversation, requiring adjustments in how we interact verbally during precipitation. The muffling effect can create intimate acoustic spaces that might facilitate certain types of social interaction while inhibiting others. The mystery of how climate change alters local rain patterns continues evolving as new data emerges. Some regions experience increased precipitation intensity with longer dry periods between events, creating feast or famine hydrology. Other areas show shifts in seasonal rainfall timing that disrupt natural cycles organisms depend upon. These changes pose challenges for agriculture, water management, and ecosystems adapted to historical precipitation regimes. Understanding and adapting to these shifts remains an ongoing challenge for societies worldwide. Rain's role in creating distinctive regional landscapes demonstrates how precipitation patterns shape visible geography. Rainforest density, grassland extent, desert sparseness all reflect local rainfall amounts and timing. Even within regions, rainfall variations create landscape diversity, from lush valley bottoms to drier ridgetops. These connections between precipitation and landscape illustrate fundamental ecological principles about how water availability determines what can grow where. The mystery of phantom rain, where people report feeling rain despite none falling, sometimes involves misidentification of other phenomena. Fog condensing on surfaces can drip like rain. Very fine mist might be felt without being visible. Psychological factors occasionally create expectations of rain that manifest as sensory experiences. These varied explanations remind us that perception involves complex interpretation of sensory inputs, rather than simple, direct apprehension of external reality. Another mystery concerns how rain influences human decision-making, from whether to carry an umbrella to major choices about travel or outdoor events. Weather forecasts and personal weather sensitivity guide these decisions, but individual risk tolerance and past experiences also play roles. The anticipation of rain can affect planning for days in advance, demonstrating how expected weather influences human behavior even before precipitation arrives. Rain's contribution to natural sound masking in wilderness areas provides acoustic privacy that becomes increasingly rare in developed landscapes. The sound of rain falling in forests creates an audio environment where conversations remain private and mechanical noises from distant civilization get muffled. This natural soundscape offers respite from constant background noise that characterizes modern life, providing acoustic restoration similar to visual benefits of viewing natural landscapes. The mystery of how rain affects sleep quality for people with various sensory sensitivities reflects individual neurological differences. While most people find rain sounds soothing, individuals with hyperacusis or autism spectrum conditions might experience rain sounds as overwhelming or disturbing. These variations remind us that responses to environmental stimuli vary widely, with what soothes one person potentially distressing another. Understanding these differences helps explain why no single approach to sleep optimization works universally. Rain's influence on chemical signaling between plants presents fascinating mysteries about how vegetation responds collectively to precipitation. Some plants release volatile organic compounds when rain arrives, potentially signaling neighboring plants to prepare for moisture availability. These chemical communications might coordinate community-level responses that optimize water use across plant populations. The discovery of such sophisticated plant interactions continues reshaping understanding of how forests and other plant communities function. Another mystery involves the formation of rain shadows on much smaller scales than typically considered. Individual mountains, large buildings, even dense tree groves can create local rain shadows, affecting moisture distribution across landscapes. These micro-scale rain shadows contribute to habitat diversity by creating drier microsites adjacent to wetter areas, allowing species with different moisture requirements to coexist in close proximity. The mystery of how rain timing affects agricultural yields demonstrates complex relationships between precipitation patterns and crop productivity. Too much rain during flowering can reduce pollination success. Insufficient rain during fruit development reduces yields. Timing of rain relative to planting and harvest determines whether precipitation helps or harms production. These intricate relationships explain why farmers monitor weather forecasts obsessively and why agricultural insurance markets exist to manage weather-related risks. Rain's role in refreshing indoor air quality when windows open during or after precipitation provides health benefits beyond simple ventilation. The combination of rain, cleaned outdoor air, reduced air pollution from damp and dust, and increased negative ion concentrations can create indoor environments that feel fresher and more pleasant. These effects, though subtle, contribute to why many people enjoy opening windows during rain despite potential water entry risks. The mystery of how rain affects photography extends beyond obvious issues of keeping equipment dry. Overcast conditions during rain create soft, diffused lighting prized by portrait photographers. Water droplets on surfaces add visual interest and texture. Rain creates reflections in puddles that skilled photographers exploit for creative compositions. These artistic opportunities mean rain, rather than preventing photography, simply shifts what becomes possible and interesting to capture. As we reach the true conclusion of our extensive journey through rain's mysteries, we've explored more than 100 distinct phenomena, each revealing something unique about precipitation's role in natural and human systems. From molecular processes in cloud droplets to global climate patterns, from individual psychological responses to societal adaptations, rain touches every aspect of existence on our water-rich planet. These mysteries demonstrate that rain represents far more than simple weather. It embodies fundamental processes that shaped Earth's evolution, enabled life's emergence, and continue supporting the intricate web of relationships connecting atmosphere, hydrosphere, biosphere, and lithosphere. Understanding rain means understanding core aspects of how our planet functions as an integrated system. Perhaps most remarkably, despite centuries of scientific investigation, rain continues revealing new mysteries. Each answer generates fresh questions. Each mechanism understood exposes deeper complexities. This inexhaustibility suggests that rain, like other fundamental natural phenomena, possesses depths we've barely begun plumbing despite its familiarity and apparent simplicity. Tonight, as you rest, may these mysteries infuse your awareness with appreciation for rain's multifaceted significance. Whether precipitation falls outside or skies remain clear, the cycles continue, ancient rhythms that predate humanity and will persist long after our species passes. In this continuity, in this patient repetition of evaporation and precipitation, we find something profound, a reminder that some processes transcend the immediate and the transient, connecting us to timescales and patterns much larger than individual lives. Sleep well, dream peacefully, and may the gentle rain of mystery wash through your consciousness, cleansing away the day's concerns and leaving behind only quiet wonder at the remarkable world we inhabit, where even something as common as rain holds endless fascination for those patient enough to listen, observe, and contemplate its many mysteries. The rain falls, has fallen, will fall again. Eternal in its cycling, infinite in its details, forever mysterious in its familiar presence.